Good afternoon. Well, I first would like to thank the organizing team for their very kind invitation to give this talk. And since it's almost the end, I can say that I really enjoyed all the great talks and interaction during the conference. So as far as I'm concerned, I would like to share some of my recent thoughts about cosmic web analysis and information theory and the connection between the two. So before diving into that, let me start with the big picture in cosmology. So the universe is highly structured at all scales. So you have here on the left observations of the cosmic microwave background as realized by the Planck satellite and released a couple of years ago. So something that looks fairly smooth as looked from if we only focus on the larger scales, but with some structure which is imprinted at smaller scales and correspond here to we believe, to quantum fluctuations imprinted on this cosmic microwave background. If we zoom in a little more, then we end up roughly the same co-moving scales, the large-scale distribution of galaxies in the universe. And these are observations realized by the Sloan Digital Sky Survey. So this is the equatorial plane. And again, something that looks fairly smooth if we focus only on the smallest scale, on the larger scales. But if we zoom in, then we end up seeing this network of clusters and filaments and surrounding the largest voids, which has been mentioned before. So for example, one of these structures here is the Sloan Great Wall, one of the largest structures known in the universe as far as of now. So these are existing observations. Of course, even more exciting observations are coming up, and not the least of which being the Euclid satellite. Right, so the question is, how do we make sense now of this structure? So let me just in one slide tell you about the approach that my collaborators and I have been developing over the last few years. So this is called BORG, which stands for Bayesian Origin Reconstruction from Galaxies. It's an inference framework in the form of a Bayesian hierarchical model. So fortunately for me, Bayesian hierarchical models have been mentioned this morning by Alan Evans, so I don't have to give too much of an introduction, I hope, on the statistics part. So let me describe this model. We start by with a Gaussian prior on the initial conditions, which is both very well supported by observations of the cosmic microwave background and by our theory for the usual theories for the early universe. These initial conditions are evolved forward, and with the structure formation model, and we end up with the total evolved matter density here, which is a functional of these initial conditions. So this is the total matter distribution, including, of course, the large component of dark matter. Then galaxy formation happens on top of that, and the biased galaxy distribution is now a model based on the full matter field. So one simple possibility is to take a power law of this matter field, which gives the underlying latent distribution of galaxies. Then we need a selection process for our observations, including, of course, the survey mask and the selection function, the radial selection function. And finally, galaxy number count is modeled in terms of a random extraction of a number of galaxies from the probability which can be written down given the selected sample. So simplest possibility is a Poisson distribution, for example. So all of that gives a very high dimensional posterior distribution, which typically lives in 10 million dimensions. This is the dimension of the map that we are trying to reconstruct. Any voxel of the map is one parameter in the problem, and it can be explored by means of Hamiltonian Monte Carlo. So this BORG algorithm we applied to state-of-the-art observations, so the Sloan Digital Sky Survey. This is something that we called chrono-cosmography. So cosmography because this is about mapping the universe in 3 dimensions, and chrono because we have the additional time dimension since the model includes a proxy for structure formation. So we applied that to the SDSS, kept about 300,000 galaxies. So this is about 17 million parameters inferred jointly. And we got around 12,000 samples. And at this time, this is really heavy computational problem. So I'm not just giving you these numbers to say that it was hard, but really becoming feasible with computers that we have right now. So at that time, it took about roughly 1 year, the entire year 2014 on the computers. So this is what it looks like. So it may be possible to show that full dome. This is video number 1. Right. So you have here on my right, on your right, observations, a slice through the observations. So these are galaxy number count in the SDSS, and we stand here. You have here the reconstructed final dark matter density field, and here on the left, the corresponding initial conditions, the two being linked by Lagrangian perturbation theory here in this case. So, it's not moving anymore. Can we loop it? Right. So once more, so this is here really Bayesian statistics in the purest sense, in the sense that any picture in this movie is one sample of the posterior PDF. So you have these stable reconstructions here in the regions covered by the data, in which data are informative, and something that fluctuates here at high redshift and here out of the survey boundaries. So we can really propagate, we can really quantify uncertainties here at the level of the map. So some of the things that can be done with BORG involve looking at the formation history of a particular structure of the local universe. So this is, for example, a look at the dynamics of the coma cluster, which relates also to what we've heard this morning from Johan in terms of other structures. So thank you for the full dome. So, and in particular, by looking into the details of the dynamic of the coma cluster, we've realized that it's in fact a cluster which is made of 3 progenitors. So you have this reconstruction here, red, blue, and green. So it's. Can we play the video? Sorry, it's not moving anymore. Right. So here, time flying backward, and you see the progenitor separation increasing, as well as their size in when it gets closer to the initial Lagrangian patch. And now, as time moves forward, these progenitors, so these proto-clusters shrink, and at some point, 2 of them merge here. So the cluster undergoes 2 major mergers. So we can have a look at this dynamic structure, and also one more thing is that BORG not only gives the density field, but also unveils the entire dynamic of the cosmic web. So here I'm showing you again the equatorial plane, and you have galaxies overplotted here on the left on the density field, the dark matter density field, and here on a reconstruction of the radial velocity field. So more precisely, what we can do in terms of the dynamics, so we have reconstructions then of the density fields. Here is a look at the supergalactic plane, and for those of you familiar with the local universe, then you may recognize some of the familiar structures. So you have in particular here the coma cluster. This is part of the Bootes void, which is actually mostly above the supergalactic plane. The Leo cluster here, you have few known clusters here in the direction of the Big Bear, Ursa Major, and Coma. And this is a filament which incidentally didn't have a name until 2016 in the literature, which we call the Virgo Bootes Hercules filament. So not only the density field I was saying, but we can have also a look at how dark matter evolves, and in particular the number of dark matter streams that converge at any given point in the large scale structure. And as expected, we get a feeling for the fact that voids are mostly single stream regions. Just one stream of dark matter there, and wherever we have galaxy clusters, then we have many dark matter streams also converging. So this is actually here only a lower limit on this number of streams, since this is at finite mass resolution. But we can say that in the densest part here in the coma cluster, at least about 5 streams at these scales should be converging at least. And we can also have a look at the velocity field. So this is here, I'm showing the radial velocity field. So you have these blue regions that are flying, they are falling towards us. These red regions are flying away from us. And as you can see, these structures are still undergoing gravitational evolution, since we have these dipoles here in the radial velocity field, wherever structures are flying. So these structures are undergoing gravitational collapse, with the matter in red here flying away from us, and matter in blue in the background falling towards us. In particular, this map is particularly interesting because when you can have a closer look at the regions where the radial velocity field is 0, and this gives a direct measurement, in fact, of the Hubble flow. any measurement of, for example, supernova luminosity here would not be biased by peculiar velocities, but we would directly have a very precise measurement of the Hubble flow. So I tried to make the point before that it is important to quantify uncertainties at the level of the map. And I would like to make this point once again by trying to show you what happens if you don't. So this is the so-called island of California, one of the most famous mistakes in the history of geography. And my point here is that maybe if the geographers at this time had quantified the uncertainties a little more carefully, the map should have looked like that, especially in this regime here. So I believe that uncertainty quantification is really crucial. So this is something that I try to show you that we can make at the level of the density field, both initial and final conditions. But is this something that we can propagate to cosmic web analysis? So I'm going to kill the suspense right now and tell you that the answer is yes. And this is actually what yields a connection with information theory. So for the remainder of the talk, I'll be talking about cosmic web analysis. So I need to spend a minute to tell you about cosmic web classification procedures. So the question will be, given at any given point in the large-scale structures, shall I call this point a void, a sheet, a filament, or a cluster? So this is also what I call classifiers. They do not focus on finding individual structures such as cluster or voids, but they really try to do everything at the same time. So still, there are many ways to do that. So here I'm going to focus on 3 of them. So the first one is what's called the T-web. T stands for tidal field. So the idea is to look at the eigenvalues of the tidal field tensor, which is the Hessian of the gravitational potential. And in particular, we count the number of eigenvalues that are positive or negative. And the number of positive or negative undervalues they tell us along how many axes we have gravitational expansion or gravitational collapse. So a void is expanding along 3 coordinates, a sheet along 2, a filament along 1, and a cluster is shrinking along 3 coordinates. So another similar idea is DIVA, which stands for dynamical void analysis. So instead of looking at the tidal field tensor, here we look at the eigenvalues of the shear of the Lagrangian displacement field. So something which is fairly related. And one last idea, which has just been mentioned before me actually, is the so-called origami algorithm, which uses the concept of the dark matter phase space sheet. So more specifically, what origami does is to count the number of orthogonal axes along which gravitational collapse has happened. So just a comment at this point, DIVA and origami are Lagrangian classifiers in the sense that if you want to apply that, you need not only the final dark matter density field, but you also need the corresponding initial conditions. So far, the applicability of this algorithm to real data was actually fairly limited. But with now state-of-the-art Bayesian algorithms, we also have access to the initial conditions that give rise to the observed structures. These are now usable in real data. So we can have a look at what these different algorithms gives on they give on reconstructions from the SDSS. So I'm here showing the three different algorithms. So T-web, DIVA, and origami. You have here voids and sheets. Next slides are filaments and cluster. So what you are looking at here is really probabilistic maps in the sense that you are looking at the probability of detection of any of these structures at any given point. And the probability for all the different structures will sum up to 1, obviously, at any given point. So here, in particular, what can be seen by eye is that the T-web and DIVA, which are related algorithms, give fairly similar answer for voids and for sheets. Origami tends to classify most of the volume as a single stream region, so as a void. And now if we look at the more complex structures, so here filaments and cluster, we have this network of filaments, which is quite clearly seen in the T-web and DIVA. These clusters, very sharp here in particular with the T-web, and they are also visible here also with origami, but though more rarely identified, at least in terms of volume. So a relevant question is now, how is information propagated between the initial and the final conditions as far as cosmic web type is concerned? So this is something that can be measured in the language of information theory, and in particular we can write it down in terms of the Shannon entropy of the structure type PDF probability distribution. So here is the standard formula for the Shannon entropy. So in our case, we have so the minus sum of p log p. In our case, we have 4 possible events, which correspond to the 4 structure types. And this is quantified in units of Shannons, or bits, in fact. But I like to be a little more pedantic and say that a bit is actually the computer representation of a Shannon. And here I'm talking more about the concept and not the computer representation. So I'm going to say Shannons. So this is between 0 and 2, since we have 4 possible events. And this is also something that we can map. So here it looks like this. Maybe you can, and we'll try to play it again. Right, so here we have a map of this Shannon information from 0 to 2, 0 corresponding to perfect detection of the structure type, perfect identification of the structure type, 2 being maximum entropy, so maximum uncertainty in the structure type. So information starts at high redshift from a fairly homogeneously distributed state, and as time as a function of cosmic time, when it was playing, you could see that information follows the trajectory of Lagrangian particles, and we end up with a fairly non-Gaussian field, which actually doesn't correlate even very well, for example, with the density field. So a highly structured field where information is really propagated to the places where we can sharply identify structures. Another relevant question is, how much did the data surprise us? And this is in particular, how have we moved our state of knowledge between the prior and the posterior. So this is also something that can be quantified in the language of information theory, with the notion of information gain, also known as the relative entropy or the Kullback-Leibler divergence. So the mathematical expression is here, and this is also quantified in terms of Shannons, and this is also something that we can map for the 3 different algorithms, the T-Web, DIVA, and origami. And this is what we have learned on the structure type. So it's something as expected, which is close to 0 here where we have no observations, and which correlates with the structure here in the constrained regions. And so more about the Kullback-Leibler divergence a little later. And another question, how similar are these different classifications? So I've tried to have a hand-wavy discussion of that a little earlier, but this is also something which can actually be quantified. So here the relevant notion of information theory is the Jensen-Shannon divergence, which is a symmetrized version of the previous expression. So it's a symmetrized version of the Kullback-Leibler divergence. And if you write down the mass, then you will realize that this is a number also in Shannons between 0 and 1. So here it can also be mapped. And as you can see here, we have now a quantitative version of this good agreement that I was discussing between the T-Web and DIVA, and a more quantitative analysis of the disagreement between the T-Web and origami, especially when we are out of the voids, which are underlined here. More about the Jensen-Shannon divergence a little later. Right. So the last relevant question is, which is the best classifier? So decision theory is a framework which allows to classify structure in the presence of uncertainty. And here the question will be, can we extend the decision problem to the space of classifiers? So the idea will be to maximize a utility function, which can be written here as an expectation of a joint utility between D, the data, T, the classification, and Xi, a classifier. So we are in the space of classifier, and we want to maximize this utility for our purpose. So an important notion will be the mutual information between 2 random variables, since this is the information theoretic definition here. So it's the relative entropy between the joint probability and the product of the 2 probabilities when we have 2 random variables. And an important property is that these can actually be phrased as an expectation. So it's the expectation of P of x given y from P of x. So in other words, it's the expectation of the information gain between the posterior here or the prior here, or the conditional distribution here from the unconditional distribution here. So this will be an important property in the following. So I was telling you which is the best classifier, and as you may expect, the answer to this question actually strongly depends on what we want to do with the classifications. So I can think actually of three broad types of problem in Bayesian statistics. One is parameter inference, second one is model selection, and the third one will be prediction of new data. So we can have we can actually write down utilities for each of these different applications. So let's try to go through this. So the first one is the utility for parameter inference. So typical question is, which is the classifier which produces the most surprising or informative cosmic web maps when looking at the data? So here we can write this down in analogy with the formalism of Bayesian experimental design. We want to maximize the expected information gain on our cosmic web maps. So here is the expectation gain on T, the classification given the classifier, so the posterior probability here from the prior here. And if you use this property I was mentioning of mutual information by taking the expectation here, you realize that what you're trying to maximize is in fact the mutual information between the classification and the data. Second type of problem is model selection. So typical example, the dark energy equation of state. I have different dark energy models, and I want to know which classifier will best separate the different dark energy models if I try to infer the underlying properties, so typically the dark energy equation of state. So here, the Jensen-Shannon divergence between the mathematical properties that the Jensen-Shannon divergence between posterior predictive distributions can be used as an approximate predictor for the change in the base factor. And this change in the base factor is actually what we want to look at when we do model selection. So in analogy with this idea, we can write down our second utility as this Jensen-Shannon divergence here between the posterior probabilities given the two models. And if you take the expectation of this, and again use this property of mutual information, then the second utility will be the mutual information between the model classifier and the mixture distribution, which is written down here. It's the mixture distribution between the two posterior distribution given the two two possible models. And last type of problem will be the prediction of new data. So far I've used galaxy as just point particles, and I've used only their clustering. But galaxies are not point particles, and they may have properties, and simplest property I can think of is a color. So to make it simple, even simpler, let's say just blue or red. So far we have not used galaxy colors, so which classifier which predicts them best as a function of their environment. So here we want to maximize the expected information gain on some new quantity, which will be C, so C is the color of this new quantity, and we want to maximize the expected information gain of the posterior probability of C given the data, the classification, and the classifier from the prior here, which was the prior just on the color, on this new quantity. And again, using this property of mutual information, if you take the expectation here, then you will realize that this third utility is the mutual information between predicted data and classification. So actually all of this can be recast in the language of supervised machine learning. It's a supervised machine learning problem. We have different features, they correspond to the different classifications. We have possible values for these different features. Here they correspond to the different structure types, and we are trying to learn a class label. So the full catalog looks like something like this. We have the different classifications, a value giving the structure in each of the entries here, and the class label that we are trying to learn. So we can actually write that in terms of the different classifications. Here, these are the different classifiers. Here, voids, sheets, filaments, and cluster, and write down the information gain for all of these. So here, this classifier separates a bit the red galaxies. It has some information gain. Here, this one did very poorly because it didn't separate blue and red at all. And here, this one did so information gain of 0. This was the worst. Here, this last classifier completely separates blue galaxies and put all of them in void, put all the red galaxies in clusters. So this is in this simplest case was the best classifier with an information gain of 1. Just one word of advertisement before my conclusions. This is advertisement of the Aquila Consortium, founded a couple of years ago for Bayesian large-scale structure inference, and which gathers people now so we are a small team, but rapidly increasing with people from the UK, France, Germany, Sweden. Anybody is welcome. It gathers people interested in developing Bayesian pipelines and running the analysis on existing data and preparing for the next experiments. So please have a look at our website and get in touch. So conclusions. BORG is a Bayesian inference engine which allows the analysis of the large-scale structure and its formation history. Thanks to BORG, the cosmic web can be described using various classifiers, and I've had a look at 3 of them. This cosmic web analysis yields data-supported connection between information theory and cosmology, which I found interesting, and I'm still interested in. And this decision theory offers a framework to actually optimally choose in the space of classifiers, depending on the utility, so write down a utility depending on the desired use of these cosmic web maps that we can now produce. I thank you.
Thanks very much. Questions?
First, thank you for really using information theory in a talk on an information conference. You went through a lot very quickly, and one thing that wasn't clear to me at all is you talked about the amount of information you could gain from different models. Were you saying that